All right, so basically in this tutorial, we're going to combine everything that you've learned or that we've attempted to teach as best as we could in the 5 tutorials. So from the start to variable, definitions, to pandas, data frames, functions, and yesterday, all the different ways you can visualize data. And so today we're going to apply all these different tools to one specific problem, which is fitting data to a function, regression, but also predicting data by fitting. So we're going to look at these two different things. And I think I'll start by giving the acknowledgements. So I really want to thank both Kenny and Jordy for their careful analysis of the notebook and for their feedback. And everyone else who has participated to help organize the CHAC tutorial, so the entire CHAC master team. So the first thing I wanted to check is that we're all able to load files. So if you look into tutorial 5, I don't know if you can see that I switched tabs. If you can't see that I switched tabs, put up a thumbs down if that exists, or shout out to me, unmute yourself and let me know. But in today's tutorial folder, you'll see that there is a Python notebook and a CSV file. If we double click on that CSV file, you'll see that you have a list of indices and 4 columns. So our goal is to load that file in the notebook because we're going to do regression based on that data. So if we go back to the notebook right here, the first thing I'm going to do is just load the libraries that we're going to need. So there's a set of different libraries. One is pandas, and we saw that one in Dave's tutorial 3. The second library, which is a really interesting library that I'm introducing today, and we're going to use it for all regression models, and it's called scikit-learn. And we'll talk more about what all these different functions that I'm importing from scikit are further on. Then we import NumPy. There are some functions of NumPy we're going to use. And to plot, we're going to use plotting from the data frame, like Wes showed us yesterday, as well as Seaborn and Matplotlib. So we're loading those as well. And then my favorite Matplotlib command is make the fonts gigantic in your plots. And so to do that, you can set this single line of code at the beginning of your Jupyter notebook and set the size of font that you want, and it'll update it for all your plots. The last command that I'm putting here, we don't really need here, but it might be useful to you if you're thinking in your final project to write your own code and to import it into your Jupyter notebook. And maybe you're working in a different window in that code that you want to import. So these 2 commands here, what they do is they just reload whatever you've imported throughout the notebook without you having to re-execute that cell. So that's why I'm just showing it here in case you want to use it. All right, so I was saying the first thing I just want to check is that everyone can load the file. So what's important to note here is that if I click on that little folder right here, I'll see what I have access to. And right now I don't see my drive. And so the first thing I want to do is I want to enable Google Collab to connect to my Google Drive folder. So I'm going to click here and execute that cell, and it'll tell me you have to authorize your Google Drive to give me access. So I'll say, all right, well, what do I have to do that? So if I click that link, it opens a window and it tells me to choose an account. So here you have to make sure that you choose the account if you have multiple Gmail accounts, which is connected to the folder in which you're running your notebook right now. And so for me, it's my UW address. And here it tells me, do you want to give us access? And I'll say, yes, absolutely. I trust Google Collab. And now it gives me a code. So I'll just copy it by clicking on that little square. And if I go back to the tutorial, here it looks like a box you can't do anything in. But if you click in that box, you'll see that you can actually paste the code and then just press enter. And at that point, in the next few seconds, it should mount your drive. So basically Google Collab will be able to see all of your drive folders. Now it tells you mounted. So I say, okay, is that true? Let me refresh. And what I see is that my drive folder has appeared. The next thing I want to figure out is where is that Cheetah file stored in my Google Drive folder. So if I click on Drive, I go to my drive. I'm going to look for the CHAC 2021 event, which is a shared folder we have. I'll go into tutorials. I'll go into tutorial 5. and I'll find the running cheetah, CSV file. And if you click on the 3 dots, you'll see that you can copy the path. So if you click copy path and you go back to your Jupyter notebook, let me reduce this a tiny bit, and you paste your path. I think I'll have to re-increase because we can't see my entire line. So if you paste your path, here I had it already set up, but you would transform it into a string by adding your quotations. And then you would define a variable equal to that path. So your path might not be identical to mine. Just make sure that you have the path that you found following the same process that I just showed you right now. And if you have trouble, then write on the chat, and one of the wonderful C Hackmasters will be there to help you. So here I've defined the path, but I still haven't loaded the data. So the reason why we want to load the data is because we want to carry out this regression, where our goal is to try and fit our data to a curve. And we're going to start by looking at fitting our data to a line. So we're going to look at linear regression. But to understand that, one thing that's important is just to load the data. So as you've noticed, I've called the data set running cheetah. And the reason is because cheetahs are actually the fastest mammals on Earth. It's amazing. They can run between 50 miles per hour and 80 miles per hour. And so if you want to watch a fun video of a cheetah racing against a car, unfortunately the car beats the cheetah, but it's a great video. So go have a look at this YouTube link. It's super fun. So here, let's start by loading the data set. So how do we load it? What we're doing is we're using a pandas function, which is called read CSV. So it's specific to data that is in that CSV format that I was showing you in the previous window. And so what does it need in input? It needs the name of the file. So I call it your path to cheetah file, but if we look back at the variable I defined, it's not only the path, but it also includes the name of the file that we want to load. So it basically needs that information. So once I give that, the second information I'm specifying is in which column I have the index. So if we remember from pandas data frames, every single row in your pandas data frame has an index. And if I was to if I were to go back and look at that file again, I see that in this first column, the 0 column, I have the index that's listed. So I'm just giving that information, and now all the information is going to be stored from the file into a new variable, which is a data frame, and I've called it cheetah_df. Okay, so exercise number 1 for everyone is, what does the data look like? Can you remember how to just see what's in a data frame? So I'll give everyone a minute to think about it, and then we'll type it up. If you're able to visualize the data in the shape of a cheetah, you get 10 brownie points. All right. So basically, the idea is that all we have to do in Python is just print cheetah_df. And if I shift enter, what I'll see is a summary of what's in my data frame. So I see my index in column 0, and I see that the different columns I have are at a given time, the position of the cheetah with respect to its home, the speed at which it was running, and its energy, which is computed in kinetic energy of pounds of cheetah multiplied by velocity of the cheetah squared per hour. So we have all this data, and now we want to figure out, well, can we fit the position of the cheetah as a function of time to a function? To know what type of function we're interested in, we want to just look at the data first to figure out, is there a trend I can see from the data? So the first thing we're going to do is create a scatter plot of positions of the cheetah as a function of time, either using plt.scatter, which here I say was discussed in tutorial 4, or actually what was discussed in tutorial 4, which is using your pandas data frame. So I'll give another 2 minutes here for people to think about how you would generate a scatter plot from the cheetah_df data frame. And remember that what you want to show is, your positions on your y-axis respect to your time on your x-axis. All right. If anyone has a plot and they want to screen share it, you are also free to do that. Okay, so here what we're going to do is basically what we do is from cheetah df. What we're going to do is say it's a data frame, so I can use the plot, and then I'm going to use scatter. I want to make a scatter plot. And here we can recheck what is the definition of a scatter plot. What do I need to pass it? I need to pass it as x, the value of the column that contains what I want to show on the x-axis, and as y, what I want to show on the y-axis. So here what I have is time in hours. And I know that that's my feature because when I visualized my data set, I saw that that was the name for that input feature. And what I have on the y-axis, on the other hand, is position in miles. But I have to make sure I type it correctly, otherwise I'm going to have a typo. And then I'm going to say that I want my markers to be super big, and I want them to be color cornflower blue. And we'll discover what cornflower blue is. And I want my marker to be a dot. So by doing this, what I'm getting is the scatter plot I was talking about. And what I see is that my position on average, the longer the time, the longer the amount of time has passed between when my cheetah got out of his or her home at the beginning and the final position, the further away they get. But what's important from this plot is that we can see that it roughly has a linear trend of position respect to time. And that's why we think that one thing that could be useful to do is to do a linear regression. So the idea is, well, I have all this data, can I on average fit it to a line? And so here, if we look at this equation one, I'm saying that my position, I'm assuming that I can define my position at a given time t as a function of the slope, which is unknown, multiplied by time plus an intercept b. And how do I find what the value of m and b is? We can draw, an infinite number of lines. I could draw them, I could draw a horizontal line, I could draw a vertical line, I could draw a line with any possible value of slope and intercept. And so to find what my optimal values of these parameters, your slope and your intercept are, what I need to do is to minimize the error between the exact values, those are the blue points that you see that I extract from my data frame, and the values that I compute. But the values that I compute depend on that m and b parameter. So what I'm looking to minimize is this function, if you think about it, this error function, which is the difference in yi exact minus slope times t I, which is known, the time is known, minus b, the intercept. And because I don't want to give it I don't want my errors to cancel out, I take the square of that difference, right? So if my difference is negative, I still want to take into account the magnitude of that error. So I take the square of that difference and I sum over all my different points. And if you're able to minimize this function respect to minimize this error by finding your optimal values of m and b, then you'll find your best fit to that data. Okay, so now I have a question for everyone, and I thought we could use poll everywhere. So there is a poll ev on pollev.com. We love DS because data science is awesome, and I'll just activate it right now. So here the question is, do we always want, if we look at equation 2, m and b to be large positive numbers so as to minimize equation 2? So you can go to pollev.com, we love DS, and fill it out. All right, let me see. Woo, we've already got 11 responses. Awesome. All right. I'll wait one more minute. All right, I'll go with a 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Lock. All right, let me share that with you. Okay, so most people, actually everyone agreed that no, the larger they are, the smaller the error is not the correct answer, and you are absolutely correct. Some people thought they need to be very small to minimize the error, and then most people agreed with the last one, which is no, we need the sum of differences to be small to minimize the error, and that depends on the values of yi exact. So let's go back to the tutorial and see why that was correct. All right, so if we look at our function that we have right here, if our value of m and b are large, that's not sufficient. And the reason is because if your yi exact is small, then when you're taking your square, you're still getting a large value. So you would still get a large value of error. Contemporarily, same reasoning, if your m and b are really small and your y exact is really large, then you might still be making a large error. And so all in all, really the only thing we can say is that we need the sum of all these differences to be small. All right, so now we want to fit the cheetah's position in time to a line. So what we're going to do is use from scikit-learn the linear model linear regression function. And so the way this function works, here if I click here, I think I have to do a select click. All right, so you can see how it works, how you define it. So what I'm actually doing here is I'm defining an object. So reg is this object that contains functions and also values. And so if we look down here, what we'll see is that when we define this object, what we can do is we can fit it, and it contains quantities such as coefficients and an intercept. And specifically in our case, we'll see that our coefficient ends up being our slope and our intercept ends up being, well, the intercept. All right, and we say that it's an object, and the reason is because it contains both functions and values. And if you want to see more about it, you can go look on scikit-learn on the linear regression page. And here you'll see that they describe a whole bunch of different linear models, and they'll show you how they're defined. But if we go back to the tutorial, the first thing that we're doing is we're creating a default empty object. So there is no value for the slope. There is no predefined value for the intercept. And then we want to fit our data using that linear regression model. And in order to do that, it turns out that what that model takes in input, it takes your features in this shape. So you need n samples, that's your number of rows, and n features, that's your number of features. And on the other hand, for the y variable, that's the value we're trying to predict, that's the position, or we're trying to fit to the position, then it needs the number of, again, rows and the number of targets. So right now, this concept of targets might be really abstract. but it'll start making more sense when we move on further on at the end of the tutorial onto looking at predictions. But here our target is only one value, the position of the cheetah. So our number of targets is going to be 1. And because that function requires the input variables to be of that shape, we have to reshape our value. So what we're doing is we're saying, okay, my x parameter is going to be from my cheetah data frame, time, the values of time. So I'm taking my data frame, I'm selecting my column, and I'm selecting the values in that column. And then I'm reshaping it to make sure that it has the shape that is desired. By putting -1 here, what I'm saying is that from the array that I have of time, take that length and create an array that is that has that length, let's call it n rows. And by setting the second element to 1, on the other hand, I'm saying, and it'll have 1 column. So I'm transforming my array to shape n times 1 by using that -1. And I do the exact same thing for y. So here I'm going to execute that cell, and I'm going to see and check whether that was actually true. So the first thing I'm going to do is I'm going to see what was the shape of this variable before I reshaped it. So I'm saying print the shape of cheetah df time in hours before reshaping it. And then right under it, I'm asking it to print x and y, the shape after I've reshaped it. And so what you see is that initially you basically had no second term here, and that's because you had a single row of values of x. And so basically, if we, a better way to understand it is probably here if I do print cheetah df time in hours, and I print the values, and I'm only going to take, let's say, the first 10, just so that we can see what it looks like. What I see is a single, basically, array, right? So it's long 10. On the other hand, if I print right after that x from 0 to 10, what you'll see is that it has basically transformed your list that you had as it was listed before. Well, let me add I should have added a new line between these, but it starts right here. Okay, so your first element is 59, but you can see that it's transformed your row into a column, pretty much. All right. So we reshaped it, and if you want to test why I'm spending all this time explaining why we need to reshape it, you can try and rerun and run the next cells without reshaping, and you'll get an error message. So the next thing we do is we take our regression object, which currently has no value for coefficients and intercept, and we fit it to the data. So we call the function fit, which is part of the regression object. We fit it, and once we fit it, the values of the coefficients, which is your slope m, and of your intercept b, will have been updated so as to minimize the difference with respect to the exact values that you have in x and y. So we do this, and we find the value of our slope and of our intercept. And now, as an exercise, I'm going to ask you to go ahead and try and estimate your value of y using the value of m and b that we found. So here in the hint, I say, okay, think of using your regression coefficient. I guess one thing I didn't show you right here is first, okay, what is that regression coefficient? What does that look like? Okay, so if I print reg coef just as is, I know that that's a variable that's part of reg. If I print that, I see that I have a list of lists. And that's why, but it only has one element. So that's why here I say I'm going to extract that element by saying from that list, if I do element 0, what I get is the first list and the only list in that case that is in that external list. And so if I want to get the value in that list, the first value in that list, then I have to access it as following because I'm accessing an element in a list of lists. So now I have m. And similarly, if I print reg.intercept, here what I'll see is that I have a single list. And so I can directly access the coefficient in there, not the coefficient, sorry, the intercept, by taking the first element. All right, so I have M and I have B, right? So the equation for a line is y equals mx plus b. And so that means that my calculated value here is going to be equal to m times x plus b. I could have also written reg coef underscore 0, 0 times x plus reg dot intercept underscore 0 here. But to simplify things, I just redefine two variables as m and b. All right, so now I've computed my fitted values of y. Another way to do this, instead of doing it following just mathematically the equation that I know describes a line, would be to use the predict function that is defined in the regression object. So it's called a predict because what we'll see in a minute is that although here we're using all of our x data and all of our y data to make the fit, it is also possible to use just part of our x data and then to predict what the y would be for the rest of the x data. And we'll see an example of that. But right now, these two approaches, line 20 and line 21, should be absolutely equivalent. And we're just checking that that's true. So now we say, okay, we fitted our cheetah data to a line, and let's see how well that line, basically fits our data. So I just make another scatter plot, the same one as before. This time I'm using matplotlib plotlib imported as PLT to make the scatter plot. And because I like cornflower blue, it's still cornflower blue. And I can keep adding things to a plot until I type plt.show. So here I first create a scatter plot, and then I define a name for my X label, a name for my Y label. And then after that, I add two more quantities that I want to plot. And so here what I'm doing is I'm saying, plot my calculated using reg.predict values of Y respect to X, which is your time, only one value right now. Not one value, but one array. And then on the second, and I'm printing that line, I'm plotting that line in red or crimson. And then the second one is the one that I checked. So in terms of computing it as the extracted coefficient, the value of m and b from my regression fit. And I plot them one on top of each other, and I see that they match perfectly. So now I'm like, all right, cool. I know that reg.predict actually computes my values of y on the optimal by using the optimal values of these coefficients. And I see that it looks pretty good, but at this point, we're just looking at things visually. And as scientists, what we really want to know is how much error are we making, right? So how accurate am I going to be if someone tells me, look, I've waited 95 hours and I just saw a cheetah? Can I predict using that linear fit the position at which that cheetah is going to be? So what we need to compute is the error that we're making. And so the error is going to be, can be computed using the mean squared error. And what your mean squared error computes is basically the sum of the squares. So you're looking at your difference between your exact values, yi exact, minus your calculated values. So here I'm going to take my m from my reg coefs, and then b from reg intercept. And then I'm going to sum over all the different data points that I have in my data frame squared, and normalize it by the number of time points. And the reason why I normalize it by the number of time points is because that's equivalent to the number of data points that I have. And I want to average it over the total number of time points, because that way I know on average how much error am I making for a single data point. All right, so how can we compute this? It turns out that scikit-learn has a wonderful function for us, which is called mean squared error. So all you need to give it is the two different arrays of values. So basically your y exact, that's the first one, and then the y that you computed. So here I'm using the y that I computed with y calc. you have to make sure that they're the same size, right? Because if they're not both 200 by 1, I think, well, I was showing it a minute ago, if they're not both the exact same size, then as you're doing your sum, you're going to get into a problem at some point because they won't be able to keep taking the difference between the two points. All right, so now we compute the mean squared error, and we see that the number is pretty large. But if we go back and look at this plot right here, you see right around this area that maybe quite a few of these points are about like 500 or 800 away in units of miles from the line. And so if you sum over all these differences squared, you can easily get to a large number. So it's always important when you're looking at these values of error to look at your actual values of position to see if the numbers that you're getting are making sense. Another way to look at the error is using this so-called regression score. So what is this regression score? It's defined here in equation 6 as this 1 minus a ratio of two terms. And what is that ratio? If we look at the numerator, it's basically the same numerator as we had for MSE. So it's the difference between your exact data points and your calculated data points, squared summed over all points. The denominator, on the other hand, is the difference between your exact data point and your average exact value of y. So in your denominator, you basically have your fluctuations of your exact data respect to its own mean. And in your numerator, you have your difference between what you're predicting or calculating using your fit and the exact data points. All right, there's a whole bunch of other ways you can estimate error, but for today, we're going to look just at these two, and you can see a list of different regression metrics here. I put a link. You can go have a look at them. But now I'll activate I think this is supposed to be question 2, and it got upgraded to question 3. But the question is, do we need a large value of SS tot to minimize R2? Is this something which we have the power to control? So I'll activate the Collab, and you should be able to respond now. I think one thing I forgot to mention, which I mentioned in all tutorials, is that only my screen and audio are being recorded. So I know it's Friday night, but if you feel like you want to turn on your screen, and on that note, my very own grad student just turned off her screen. No, I'm joking. Nira disappeared, but feel free to turn on your videos, and I'm happy to see you. You're not being recorded. Nira's back. All right.
I'm back. Sorry, that was really bad timing.
Don't worry, I just thought it was perfect for my joke. You're also free to keep your videos off, so. All right. Let's see, I have 9 responses. I'm gonna wait to reach to a 21 like we had last time. And if you've already responded, I really recommend that cheetah video. It's pretty cool. When I was watching that video the first time, I really wanted the cheetah to beat the car, and it does, like right until the end, but it's a pretty powerful car that they have there. All right, we'll go with 1 more minute because we're at 18. So technically we only need 3 more responses and then I'll lock it.
Hey, Stephanie, how is the total sum of squares related to variance? Is that, it looks quite,
Yeah,
is that?
We're going to see that. That's a really good point. We're going to see that in, like, I think 4 cells. But
Awesome.
your MSE, like, yeah, you can rate it like your bias squared plus your variance. So it is connected.
Cool.
Yeah. All right. We're at 20. Okay, Nita, fill it out so we get to 21. All right, let me share the screen with, okay, I'm on the wrong thing, that one. Let me find that. Okay, I have too many browsers. Aha, found it. All right. So, okay, that was the last question, but if we go back, we can look at question 2. All right. Open Sesame. Okay, do we need a large value of SS taught to minimize R squared? Is this something which we have power to control? All right, I'm surprised only 2 people wanted to get back to the cheesecake, so it means we're doing pretty good. But so we have, okay, yes, the larger it is, the smaller the ratio. If the ratio is small, R2 will be closer to 1. So that is in part true, but we'll get back and look at the equation and see why it's not overall like universally or generally a thing that'll work. And then the second option we have is no, because the numerator might be huge and therefore it's not enough for the denominator to be large, we need the ratio to be small. So that pretty much summarizes it. But let's go back and look at the notebook and see why the second one is 1. That would make more sense. No worries, you're not getting graded on your answers. So I love wrong answers. That's how I learn. Let me get back and share the notebook. All right, so if we go back to the notebook here, what we see is, again, yes, we have that ratio. The problem is that our SS taught, that really is something that we don't really have control over. And the reason why that is because it's only based on the exact data. So our mean here that we have is the mean of the exact data. So those are the fluctuations of your data. And so what we really want to do is mostly minimize SS res. So that means that overall we want to minimize the ratio of one respect to the other. One thing that's interesting about R2 is that it could be negative. It's not necessarily a positive value. And that's because if your SS res is really large, then your ratio might end up being larger than 1, and then you'll get a 1 minus a number larger than 1, and you can get a negative number. All right, so let's see what our R2 score is. What we really want it to be as close to 1, so let's hope that that's the case. Great, we can pretty much predict our cheetah's position without too much trouble. But now I keep saying predicting, and what we've done up to now is just fitting. But one thing that's really interesting to think about is, well, let's look at that data again, right? If we look at this plot, well, maybe we could think that, what if we only fitted our line using a slice of that data? Would it be possible to use whatever model we fitted on, let's say, all the data up to 75 in terms of time in hours, to predict the data in the last slice? If we could do that, then that would be great, because then someone could just come to us and say, look, I've been waiting for 80 hours. Could you on average tell me where you think the cheetah is? And that's the idea that's also behind a whole set of methods which are known as machine learning. The idea is very often it might be difficult to get all these data points. So here we have, an inspector who's been exploring the savannah for like years and years and like chasing a cheetah to get its position, and it took a lot of time to get all these points, right? But what if it was possible to just predict them without having to do, all of that extra work? Then at that point we would have something really powerful in our hands, which would really help us to make predictions more rapidly. But then the question becomes, well, how can we quantify our error, right? Part of the error could be just noise from the fact that maybe we're not measuring correctly where our cheetah is. Part of our error could be, well, am I using the best model possible? And then another part of the error could also be, well, am I selecting the right part of this overall data set to be able to train my model to predict where my cheetah is going to be in time? And so all these different pieces of error fall into what's called irreducible and reducible error. So the noise in your measurement, that would be your irreducible error. It's an error you can't avoid and you have no control over. But the error that's related to your choice of model to fit your data, or the choice of the slice of your data to train your model or to fit your model, that's called reducible error. And it can be broken down into these two pieces, which are called bias and variance. So right now what I'm going to do is I'm not going to tell you anything about what bias and variance is. And we're going to go through an example, which will show us, what variance is from the example. I think it's easier to understand that way. And then we'll go back to define from that example what the variance was. So if we go back to the problem of our cheetah, one thing we were just bringing up a second ago was, well, what is the most important part of my data to use if I want to make a prediction? So let's see what happens if I choose different parts of my data and create a different fitted line on each of these different parts of data. How different is my final model linear function going to be? So we go and take our initial data set. So here I'm just pasting every time the code in case you're trying it out. That way you can go back and take it back. The way we're going to do it is we're going to look at our data set and we're going to do just something simple. We're going to say, all right, we're going to decide that we want to predict this area here. And then we're going to take as training data set a slice here, a slice here, and a slice here. So we're going to train one model only on this data here, one model only on the data here, and one model only on the data there. And so to do that, we need to create these so-called training data sets. So from our overall data, we're going to divide it into a part we train on and a part we test on. Okay, so let's look at how to do that. So here, what I'm going to do is, as I was showing you in the plot, I want to select my data based on the value of time. So time is stored in the x variable. That's where we stored it up to now. And so in this complicated line right here, what I'm doing is I'm using to begin a function from NumPy, which is called np.argwhere. What does that function do? What it does is it'll look in a NumPy array and it'll search for indices for which the values satisfy this condition. So let's look at an example to understand that line better. So if I print the first 10 values of x, I see that these are the values. And so here what I want to figure out are what are the indices in that array for which the value of x is smaller than 35. So if I look at that list, I can tell, for example, that here the fourth term has a value of 20, which is smaller than 35. Okay, so now the next thing I'm going to do is I'm going to print numpy.argwhere. I'm going to search. I'm going to take my whole list. I'm going to pass it the list, and I'm going to say, give me all the positions, that's what argwhere returns, for which the value of x is less than 35. So if I do this, now I see I have a whole long list, because here I gave it the whole list of x. But interestingly, the first thing I note is that it did go and pick out the fourth element, right? And it gave me as position 3, 0. The reason why it gives me 3, 0 is because if you remember, we reshaped that array to be of shape n times 1. So it's saying row 4, column 0. All right, so now we have indices, and now we say, okay, we have these indices. Let's go back let me just re-execute that cell. That way we don't have that super long list anymore. But if we go here, now we say, all right, when I run this, what I get in output is a long list of indices which each have 2 positions. One is the row and the second is the column. But all I really care about is the row, because the column is 0 for all these different values. And so now I'm going to go and grab basically the first element of each of these lists, of each of these indices. So here I'm saying, create a list where each element of the list is int 0 for end in my list. So if you think back of the list that we printed to the screen before, what's happening is I have a for loop that is basically iterating through that list. Each element of that list is called end, and end is always a list with 2 elements. So I'm saying, as I iterate, take the value, the first value of these 2 elements. Let's see if that worked. So we know that there was one element that was 3, 0. That was the first one. And we see that we got a 3. So it did what we wanted it to do. And you can go back and reprint just np.argware, and you'll see that all that happened is that it basically converted your list of 2 elements into a single list with 1 index. Now, the reason why we did all this contorted process right here is because we want to be able to pass these indices to our overall x and y to extract the values at those positions. And now I said, okay, my training data set is, my testing data set is going to be 4 times less than 35. And then I defined 3 training sets. So I'm going to train 3 linear regression models, one between times 35 and 50. So here I'm setting 2 conditions. So I'm saying first condition, x has to be greater than 35 hours and less than 50 hours. Second condition is x has to be greater than 50 hours, greater or equal, and less than 70. And the last one is 4 times greater than 70. So I've defined, by doing this, indices of positions from my data frame where I know that these values are true. And having defined these indices, now I can go and pick those points and save them into an x1 train, which is in indices 1, x2 train, x of indices 2, and same thing for y. Okay, so we do this, and by going through this process, we've defined basically a new NumPy array, 3, or actually 4, let's make that 8. All right, 8 new NumPy arrays. The x's are times within specific ranges of times, and the y's are the corresponding values of the positions at those specific times. And we did this by selecting the indices. Okay, but it's always good to check that what we did was correct. And so here what we're going to do is we're going to plot these values that we've just defined just to make sure that what we did was actually what we had in mind. So here I'm going to use the plot.scatter, and I'm going to put x1 train, y1 train, same thing, x2, y2, x3, y3, and also the test set. And I've decided to use some super funky colors. So I have one that's royal blue, one that's Indian red. There's even medium sea green as a color. And if you want to see all the colors, just look for matplotlib colors. It's amazing how many colors you can get. One thing that I'm adding here that Wes mentioned yesterday, but we didn't really have time to get, he didn't really have time to get into the detail, is the legend. So here I'm adding a label here. It's a string to say what that data is. So here I'm saying it's train data set 1, train set 2, train set 3, test set. And to see these labels on the plot, I have to define a legend. So I add this command, plot.legend. And here I say that I want to put, this you don't have to do. These are just, you know, fancy commands of where I want to put my legend. You could just put plt.legend. But I really want it to be outside of my box. So I put it at a distance of 0.8 outside of the box and on the upper right-hand side corner. All right, so if it all went well, then I'm super happy and I'll say, woohoo, all right, great. I don't see any overlap between my points. So I've defined a test set. That's where I'm going to test. And I'm going to train my first linear regression on the blue area, my second linear regression on the red area, and my third linear regression on the blue data points. Sorry, the green. All right, I can still see colors. All right. Okay, so now we have to proceed just like we did before. If you think of when we looked at the whole data set, we're doing the same thing, but we're just going to create 3 different objects. And the reason why we have to create 3 objects is because the moment we fit, the values of the coefficients and of the intercept get updated. So if I had created a single regr and then called regrfit 3 times in a row on each data set, the value it would have stored would be the last one from the last fit. So we have to be careful and make sure that we're creating 3 different objects. So I create the first one, and here I say train it on the first data set and store the optimal values of slope and intercept into this object. And then I do the same thing for reg2, but in this case, I'm going to train it on x2 and y2, so I'll have a different value of m and a different value of b, which will be stored in reg2. And I repeat for reg3, and now I say, okay, again, if I were to print here reg1.coef, what I would see is just like before, because I'm only looking at fitting position respected time, a single list of lists. So I can access my m coefficient as taking, I'm in my list, I'll take the first element of my list. The first element of my list is a list. So once I've typed reg1.coef_0, I'm in the first list, and then I want to get the first element in that list of lists. So that's why I'm accessing it this way. And I do the same thing for the 3 different objects I've created. So by doing all of this crazy process with indices, I've basically fitted a linear regression on 3 different training sets. We saw where they were on the plots, and we obtained the optimal value of m and b for each of these 3 sets. The next thing we want to know is how good did we do? So to know how good we do, what we did in the past was we predicted on the entire X test. So we weren't really predicting, we were just fitting. So we were just computing what our computed values of Y were once we had trained on the entire set. But now we divided our initial data into a part to train on and a part to predict on. So now we are actually predicting. We're taking our X test, which is the gray area here in this plot, which none of the models that were fitted on the other areas have seen. And we're going to look at how well model for 1, model for 2, model for 3 predicts these data points. So here we basically call the predict function, but you could also write, if you wanted to, m1 times x test plus b1 for the first one. For the second one, you could also write m2 times x test plus b2 and so on. But since we already checked that predict works, we're just going to trust it and use predict to reduce the number of lines of code. All right, so we created now values of y, and we want to see, what do these lines look like? How accurate are our predictions? So we're all of the models are predicting in the same area. And so the length of ycalc1, ycalc2, and ycalc3 is identical because we're for the 3 models, we're predicting on X test. So now we're going to make another plot. And so here, the first thing that I do is I plot the exact positions respect to time. So that's just X test and Y test. And here I decide I want a circular marker of size 100, and I want the face color of my marker to be light gray and the edge colors to be slate gray. And that's what happens when you have enough time to spend on adjusting all the colors of your plot. But if you want to, you can do that. And then I give it a label. I say that's my test data. And then I say on the x-axis, the label is going to be the time, and on the y-axis, we're going to have the positions. The second thing that I do is I want to see, on average, if I combine the values from these 3 models I just created, and I compute a calculated average, what does that look like? And how different is each of my models from that average? So here I compute the average just by summing the computed value 1, 2, and 3 that we just computed a couple of cells ago, and I divide it by 3 because it's from 3 different models. And now I plot everything. So what we're going to plot is our X test, and then what I obtained from model 1 in blue, and then what I obtained from model 2 in red, from 3 in green, and then the average, we're going to add that as well in a dim gray. Apparently that was a color I found fun at the time. All right, so what do we see? What we're seeing in gray circles is the test data, this exact same data I was showing you in the plot above. And as you can tell, we're only predicting up to about 35. And what we see is that, for example, linear fit 1 is pretty close to the average fit. Linear fit 2 is a bit further apart, and linear fit 3 is much further apart. And so if we look at the average, the models can all be quite far away from the average. So there's quite a bit of variance respect to that average. So basically what this plot is showing you, well, actually that's your next question, so I won't tell you. I'll ask you the next question and then we'll get back to the answer. Well, let me activate the next Collab. 1 second. All right, that should work. So here I'm asking you, why do you think each linear fit has a different slope and intercept? And you can go and fill out the quiz. All right, 1 more minute. If you're wondering if this is real cheetah data, it is absolutely not. I think one thing to bear in mind is that they would never resist to keep running at 80 miles per hour for 30 hours straight. That would be pretty impressive. All right. Let me find. All right, let me lock it at 18. I think we've always got 3 people who are eating, cheesecake, so it takes time to get to the total. All right. Okay, so here the question was, why do you think each linear fit has a different slope and intercept? So response 1 was because we created 3 different regression objects. That is correct. But it's not enough to just create 3 different regression objects. You also have to fit them. So it's partially correct. And then the second one was because they were trained on different subset of the training data. And that one is correct. So unless your so-called variance is 0, then you're always going to see a variation in the model that you obtain as you train on different areas of your set. And let's go back and look at it. And now we can actually define what variance is. Okay, I just have to get out of the Zoom full screen because I can't see my Jupyter notebook anymore. All right, I found it. Okay, so if you look at these lines, the green, the blue, and the red, the green is above the gray, the blue is below, the red is below the blue. If we go back up and look at our data set here, what we saw was that the green was the worst at predicting. But that kind of makes sense when we look at the data, because we see that green is so far away from that area. So if I were to try and fit this to a line, it's likely that the slope is going to be really different respect to that area down here. And on the other hand, blue is the closest. And so in this case, blue is probably the best at predicting respect to the gray. But it also shows us that, because of the way I selected the training data, I can get a large difference respect to the average of each model. And that's what's your variance. So your variance tells you how much you're learning based on your training set. All right, and now we'll look at a different type of error that you can make, which is bias. So in the case of bias, we're going to start by defining, someone just came down from a cloud and told us the true cheetah function, they knew it exactly, as a function of time is this one that I've defined right here. So they say, the exact position of your cheetah as a function of time, if you were to remove your irreducible noise, then that's what you would get. Those are the magic numbers. So we say, all right, great, we have our exact function. And now the next thing we say is, well, let's see what my average value that I obtained from the 3 models above, how that differs from the true cheetah function. And if we look at that, what I'm doing is, again, just plots and then the scatter of the data on the test set. What I see is that I'm off from the true cheetah position by a certain amount. And that amount is what we call the bias. And so the idea of bias and variance are the following. Bias is how much error is your choice of model making respect to the true curve that describes the data. On the other hand, variance is telling you how much does the specific training data set that you choose to train your model influence your final model. And so it turns out that if we look at this plot right here, one might think that, maybe I can improve my bias, make it smaller, by using a more complicated function than a line. So maybe I could think of using some type of parabola, or not a parabola, that would be a terrible choice, sorry, some type of like polynomial or something like that to basically follow the data better. So I could increase the complexity of my model to improve that. But on the other hand, if I increase the complexity of my model, then what might happen is that if I look at my data right here, I might have a function here that predicts and goes through all of these different points here, which is completely different from one that goes through all the different blue points, right? And so that leads to this concept, which is called your bias variance trade-off. And so I have a plot that I made at some point on my tablet. I'm showing you right here that if you're overfitting, so if you're learning too much from your data, that will lead to a high variance. So you strongly depend on your data set. But that doesn't really get you to the trade-off yet. I'll show you the trade-off in the next plot. On the other hand, if you're underfitting, so if you're not learning enough from your data, you might be really biased from your true curve, which describes your data. And so what happens when I was talking about model complexity, it might be that if I have a very simple model, it won't depend so much on the area of my overall data set that I'm using to train to basically model it, right? So if I have a simple model, I'll have a small variance. So if I just take a line, for example, overall, my total variance is not going to be large. On the other hand, if my function is really simple, it might not be able to describe more of the subtleties that are present in the true function, which is generally unknown, which describes the data. And that relates to your bias. And so as your model gets more complex, your bias generally goes down. But at the very same time, because it's more complex, you end up being fitting with more and more parameters each of your training set areas. And so your variance goes up. And so the sum of your bias squared plus your variance can be shown to be equal to your mean squared error. And that's where your trade-off comes from. So you want to get a model that's complex enough to reduce your bias, but at the same time, not too complex to increase your variance. And so as you're looking at different models, you can find an optimal point of complexity where you've basically reduced your bias, or you're at this trade-off point between your bias and your variance. All right, okay. Awesome, I think I'm on time, which is amazing. All right, so now we're gonna look at going beyond a single feature. So right now we looked at predicting the position of a cheetah as a function of time. However, I have this list I wrote a while back, and I thought, well, the speed or velocity of your cheetah, the position of your cheetah could depend on his or her energy that day, on how well the cheetah slept the night before, how well he or she was fed, or how much he or she has been training recently, right? So all of these are different parameters that are independent from a dependent variable v, the speed of your cheetah, but which can determine what your value of v is. So while right now we're just looking at time and position, it would make more sense to start thinking of, can I also learn information from these other parameters? And so that's what we're going to do next, but not with our cheetah. We're going to get back to the Boston housing data. All right, so you've seen the Boston housing data like 2 times for now. You must really love it. And if anyone can come up with a Seattle housing data for next year, hats off. That would be super amazing. You'll get triple acknowledgements. But let's load it again like we did in tutorial 3 and tutorial 4, because we know there are a lot of different parameters in that model. So there were a lot of different columns. And so the first thing we're going to do is just load the data set like we did yesterday. And when we load it, we know that what we're obtaining is a dictionary object, because we're using the load Boston function from scikit-learn. So then we convert that object using pandas.dataframe to a data frame by specifying the values of the columns. And then we say that the value that we want to predict is the cost of housing. So here I'm just going to load that. And now I'm going to give you an exercise that if you were awake an hour ago, you should be able to do in 30 seconds straight. Check that the data frame looks good. And if you were awake yesterday and the day before, you want to check that your data frame is looking good. And I'll give it away in 1 minute. Or if someone wants to suggest it, that would be super awesome as well. All right, no suggestions. I know everyone is still lost with a cheetah. They're like, why are we going to Boston data frame? All right, so if we want to see what's in a data frame, we can just print its name, just type its name and print, and then we can just see what it looks like. So, you know, when I say we're checking that it looks good, it's probably undescriptive. We're just checking that it is an actual pandas data frame. And we're checking that we can see, you know, all the different, oh, someone actually wrote it. High five. Thank you. Yes, we could do bostondf.head. That's even better, because then you could just see the top of the data frame. Woo! All right, so we see all our different columns. And now we're going to look at loading the data in a different way. And we're going to load it in a different way simply because we have to use the scikit-learn functions to do regression. And so here what we're going to do is we're going to load it using the return xy equals true. So here we're dividing all that data set so that the first 13 columns are considered as independent variables, just like your time. For example, when we had position equals slope times time plus b. Here our independent variables are, I don't even remember what these are, but crimson, indus, chas, nox, rm, h, dis, rad, all of these are your independent variables, and your dependent variable is med_v. So med_v will go in y, and all the rest will go in x. Okay, and so we do that by using the return xy equals true. And if we if we print x.shape and y.shape, we'll be able to see what shape these are. And we'll see that we're already getting to the type of shape that we want to use for regression. And if you want to know what type they are, so these are no longer data frames. So let's see what they are. We have NumPy ND arrays, and that's what scikit-learn wants in input. So that's the only reason why we're loading it as following. All right. The first thing we're going to do is just visualize the housing prices. That's what we're aiming at predicting. So let's see what they look like. And so here I'm using the same plotting that Wes introduced yesterday. So I said I'm going to basically plot the med_v of my Boston DF. I could also decide to just do a plt.hist of y. That would be another way to do it. But here I specify that the kind of plot I'm making is a histogram. I want 30 bins, and I decided to go with the color Rebecca purple. Another fun keyword I added here in your plot is transparency. So alpha measures transparency between 0 and 1. The smaller your alpha value, the more transparent your plot becomes. So here, for example, alpha is 0.8, but let's say I make alpha 0.1, then it becomes almost invisible. All right, but why is it sometimes practical to plot things with some transparency? Because you might want to put multiple things in a plot and you want to be able to see some data behind it. All right, so that's the values that we want to predict. And now we're considering 13 independent variables. Before, with the cheetah, we only had one, it was time. And we're going to call these input features because that's a general terminology that we use when we're looking at making predictions using machine learning. So the independent variables are called input features, and then your dependent variable is your output. Okay, one thing to think of, and here I'm bringing back the beautiful heat map that Wes created yesterday, is that sometimes one can start thinking of, well, do I really want to make a fit by using all parameters? For the cheetah, I just used time, maybe that was good enough. If I look at the Boston data frame, maybe I'm just going to need some of these input features. And one way to think about which input features might matter is to look at this Pearson correlation coefficient. And so if two values are strongly correlated, that might mean that they both contain some information which is similar in some sense. And so if they're really strongly correlated, I might not need to include both of these variables when I'm training my model. But to begin, what we're going to do is we're just going to do no prediction. We're just going to do linear regression on the entire data set. So we're going to use every single row in our Boston data set, and we're just going to apply our regression model like we did before. So we create our linear regression object, same as before. We fit our x and y. And here, x and y I had just obtained 3 rows up by extracting it using the scikit-learn function. And once I've fitted my model, I'll have a value for the cheetah. I had a value of m and a value of b. And so one thing that'll be interesting to see is what are we going to get out now? And the second thing we're going to do is also predict directly by using our updated reg object that has updated values of coefficients. So that cell of code ran just fine. And now we're curious to see, what are these coefficients and how many coefficients do we have? All right, so when I print reg.coef, what I see is now I don't have a single list with embedded in that list, another list with a single parameter, which was my slope. What I have is 13 coefficients in a list. And the reason for that is because I had 13 input features. And so what's happening? What's happening is that we're no longer fitting our output value y to a single slope m plus m times x plus b. What we're doing is m times rad plus m2 times tax plus m3 times nox plus b describes my overall y. So each of these x is a different one of the different columns that I had in my data frame, one of the different input features. And what I've determined from the fit is the 13 parameters m1 to m13 that led to my smallest error when calculating y by doing a linear regression and using all of these different input features. All right, so things are getting crazier for a Friday night. Woo. All right, so now we have 13 slopes somehow, you can think of it that way, and 1 intercept. If we print the intercept, it's always just 1. And now we're going to say, all right, let's make sure that the number of coefficients we got actually matches the number of input features we had. So we'll say if the length of my input array x along 0 is the same as the length of my regression coefficients, then everything is good. Number of coefficient matches the number of input features. Otherwise, something strange is going on. Ah, good. Nothing strange is going on. All right, they match. And now the next thing we want to do is look at how much error we're making. And so the two metrics that we've described were your MSE and your R2. We define them in equation 3 and 6. And we can use scikit-learn's mean squared error to compute our mean squared error, and R2 to compute our R2 score. So just to remind you, we want our mean squared error to be small and R2 to be close to 1. And here we trained it on our entire data set. And what we found was that the mean squared error is 21.89 and our coefficient of determination is 0.74. Again, to understand whether that error makes any sense, it's always good to go and compare it to our values. So if we go back up to our Boston data frame, here we were just listing it, right? But can anyone remind us how I would get the stats on that data frame? Is there a specific command that Dave basically showed on how to get your mean and your average for each column? Woo, at the speed of light. Describe, correct. So if I do Boston df.describe and I do it correctly with the parentheses, then what you'll see is that you have your count and your mean. And so if we go to our MEDV, we see that our average value is 22.53. And so our error is pretty big because it's pretty much on the same order of magnitude as the average of our data. All right. Let's go back down here. Where was I? Okay, and our R2 coefficient is 0.74, which is again pretty far from 1. All right. The next thing we can do is we can try and see, well, how do my computed values match the true values graphically? So here what I'm going to do is on the x-axis, I'm going to put the values that I've computed by fitting my model to the data set. And on the y-axis, I'm going to put the exact values y that I had defined. Again, I'm using like one more thing here, which if anyone has ever heard of LaTeX before, you'll find it super fun. If you haven't, ignore it completely. But if you have used LaTeX before, you can actually write equations in your labels of your plot. Any LaTeX code has to go, or command has to go between $signs. All right. So if we look at this plot, what does it mean physically? All right, so if things were perfect, what we would want to see is we would want to see all points on the diagonal. And why is that? Well, let me actually reshape this plot so that it's in a square. Let's go with 8, 8. And then let me make sure that each axis is the same interval. Let's go with 0 to 50, and then again, 0 to 50. Okay. All right, so now it's become bigger, but we have an actual square, so it's easier to understand. The reason why we would want all points to be on the diagonal is because that would mean that the value I've computed is identical to the true value. And so the more points we get away from that diagonal, the larger error we're making. So for example, here, my value that I've calculated, or so in this case, predicted from the fit on all the data set, is really far away from the true value. Here I have about 38 or something like that, and the true value is around 22. Okay. And now what we're going to do is we did the fit on all the data. And so as the last thing we're going to look at today is let's look at making predictions of the housing costs by taking only part of our initial data as a training set. And so what we want to do, you can just think about it as you have your whole data frame and you have a whole bunch of different rows. And so you want to select some rows. Let's say you have 10,000 rows. You might want to select, I don't know what I said, 1,000, right? Okay, so 600 rows as your training set and 400 rows as your test set. And luckily for us, scikit-learn has a train test split function. So you give it an input, your x, your input features, and your y, your dependent variable, and you say, I want to have 30% of these values to be in my test set. And it's a good thing to do to select them at random. The reason for that is because if you select your rows at random, then it's more likely that you're going to be able to represent your overall data set. And another thing I can say to convince you of that is if you think back about the cheetah, my splitting just by hour was really bad, right? If I had split it randomly, so if I had randomly selected points in that interval, then each model might have made a better prediction. And so here when I set random state equals 9, that's related to the fact that, all right, you've probably heard of random numbers before, right? So one of the biggest computational problems is creating random numbers. So you can't create true random numbers. You can only create these so-called pseudo-random numbers. And so there are these algorithms that create these pseudo-random numbers, but the idea is that they'll be able to create, let's say, 10 million almost random numbers based on an input seed. So this almost sounds like I'm growing a tree here, but the seed is the initial value you give to that algorithm so that it starts creating that super long sequence of random numbers. So here when I say random state equals 9, I'm specifying it so that if I rerun this, I'll always have the same set of random numbers, and I'll be able to check that I did everything correctly. Okay, so what does this function do? It takes the whole data set and it splits it into 70% chosen at random that goes into training, 30% chosen at random that goes into tests, and the corresponding, so same rows, values of the output value, which is our house cost for the training set and for the test set. So one thing I think is always good to do is to check. So we want to check, they say that this function works, it looks pretty cool, but do we really trust it? So one thing to check is, if I sum these two together, if I sum the length of these two, that should give me the length of y in my entire data set, right? So I just want to make sure I didn't skip any points. So I'll say, all right, if the number of points in test plus number of points in train is equal to the number of points in my overall data set, all right, I'm good to go. Things worked out. And then I'll say, at that point, if everything is good to go, then I'll run my linear regression model on the X train and Y train and print out my regression coefficients and my intercept. And once I've done that, then I'll use, just like we've done before today, the predict function to predict on the test set. One thing that is really important, and I don't know if I emphasize it enough, is that your model should never see the test set until it's trained. Because if it sees a test set, then it's getting information from the test set. And at that point, it'll make a really small error on the test set, and you'll be fooled into thinking that your model was trained better. What we want our model to do is to train it on data and then to predict things it has never seen before. The reason why, in this case, we split our initial data into train and test is because for our test as well, we know what the true answer is. And so although the model has never seen it before, we can actually, as inspectors, be like, hey, are you doing a good job or not? All right, so let's see if it did a good job. Okay, so right now, we don't know. We're not looking at the metrics of error, but what we see are the fit coefficients. And we have one for each of our input features. So 1, 2, 3, 4, 5, 6, 7, that should be 13. And then our intercept single value. And now we're going to look at what it looks like in a plot. Just like before, we're making a scatter plot, but I'm also printing right below that plot the mean squared error and the R2 score of my calculated test value respect to the exact Y value. All right, so what does this look like? This is a plot that I have. Interestingly here, my coefficient of determination is slightly better than when I was fitting the entire data set, and my mean square error is slightly smaller, but it is also true that we're looking at a smaller subset respect to the total data. But I think that's amazing here, and if you think about it, it's really mind-blowing, is that that algorithm has never seen these data points, ever. It's been trained on part of the data, and it can now predict on data that it has not seen before. And if you've seen, I think I already advertised this in like the DSMS class, but if you've seen self-driving cars, that's exactly what they're doing. You know, as they drive, they take pictures and they try and identify what's in the picture, although they've never taken that picture before. All right, so now we have maybe, I'll give 4 minutes. One thing you can do is play with the size of the training and test set and see how that changes your error. And so to do that, all you have to basically change is the size of your test set right here. So you can change it 0.3 to different numbers, rerun the subsequent cells, and see how your error changes. And then in 4 minutes, we'll get back with the rest. I think I haven't taken time up to now for questions. I just realized it's been an hour and a half that I'm talking, and are there any questions? All right. Well, if you have questions, I see some were answered via chat, but feel free to ask. I'll take maybe, oh, okay, here we go. The higher I set my percentage of points used, the worse my error seems to be getting. That is a really good point. So what's happening is if we go back up here, so here you're saying as you increase this number right here, right? So if we increase the size of our test set, basically what's happening, so let's go and increase it to 90, for example. So we have our overall data set, and we're deciding I'm going to basically train it on 10% and predict on 90%. So let's see what happens with the error. So we run it, and then we look at what our metric of error is. All right, so now we see that our coefficient of determination has gone down and our mean squared error has gone up. So I like to, so the reason why it's the error is getting worse is because basically our model is seeing less data. So it's able to learn less. And so it's basically seeing more information somehow than what it was trained on. So one way to think about it is, let's say you had to train a model to predict a species of cats, right? Let's say you have, or puppies. Dave loves puppies, so like a breed of puppies. So you have a whole bunch of breeds of puppies, and let's say you have 10 million points, and each is a puppy and the breed. And let's say you take 5 points to train your model, and you have, and unfortunately, maybe as you trained it, you only ended up with 2 breeds of puppies. But altogether, there are 20 breeds of puppies. So when you try and predict the rest of all your different points, the problem is that your model has never seen those breeds. And so it tries to predict what their breeds are based on what it has seen. And at the very same time, if I were to predict it, to test it, to make my test set be 0, then first, one problem would be I wouldn't be able to test anything, but at the same time, I would have seen everything. And so my error would be 0, but my prediction ability would also go down to 0. So that means that on average, what you want to do is have a train set which is around like 70 to 80%, something like that. There's no like perfect number for it, which is representative enough of everything that you're going to see. So let's say we know that overall there are 20 puppy breeds. You would want to make sure that in your train set you have maybe at least like 20 or 19 different puppy breeds that are represented to be able to predict afterwards. And so that was a really good question. Okay, you had it backward. Yeah, awesome. So there you go. So test, you want test to be smaller than train in general. Any other questions? All right. I think we're right at the end. I think I'm pretty amazed by timing here. All right, which is great because it's Friday night. Everyone needs some rest. All right, so next question is, do we need all independent variables? And you'll get to look at that in the breakout room right after the break. And another question could be, well, all we've looked at is linear regression. Are there other types of regression? There are. So here I list a few: ridge regression, lasso, random forests. And if you found all of this like super duper easy and you want to try them, you can try those as well in the breakout room. And they're all implemented also in scikit-learn. And here, I do not remember what I was trying to do. Oh, I think I was trying to, oh, there you go. So here I was trying to look at ridge regression. So it's another type of model. It's still a linear model. And so in this case, I'm using that model and I'm getting coefficients again and an intercept. And here I want to see, well, is my error better than when I was just using the linear regression model? And here I see that, well, it's not that great, but right now it's not that great also because I have to re-increase my test size. Let me go back to what I had before. 0.9. Oh, nah, okay. I think I had, oh, no, that's right. I'm doing my double error of rethinking of train as test and test as train. All right, so we were here. That was the linear regression. So here we had a 7.8. And now we're looking at ridge regression. And in that case, our error is, let's see, 7.8 as well. Maybe it's a universal number for this data set. Anyway, but your mean squared error is different from what you had before. So with this, in the breakout room, things that I think are fun to look at are the number and choice of input features. Do you need all input features, or is it possible that you can select a subset which is more representative or gives you a lower error than if you use all of them? And then the other two concepts that we looked at were bias and variance. So bias, we can't really compute exactly, although people have developed all these different types of approaches to break down the MSE into a bias and variance. It's hard to measure bias, and that's because we don't know what the exact function is in general. But one thing you can look at is your variance. So what you can look at is, for example, selecting different areas of your Boston data set and see how your error changes. And you can look at choosing different columns as input features and see how your error changes in that case as well. And so here I just thought I would show you, in case you want to use 5 features, what you could do is, again, we're slicing our array. So we're saying here, for example, I want to choose the first 5 features. So then I'll take from my X train all the rows, so all the data points in X train, but only columns 0 to 4, so the first 5. And same for the test. And I think here I was just printing them just to check that my shape was what I wanted it to be. And I see that it has the right shape and a different number of points because it's train and test set. And that's it. If you want to look at different types of regression algorithms, here I'm putting some other functions as well. And I've put some questions you can think about as you're working on both of these problems. But with that, go ahead and take your break. And if you still have the energy, stay with us for the last CHAC 2021 breakout rooms.